Good evening everyone, good evening. I welcome you all again to NEET Elite. I hope you guys are doing great, having a good time. Sorry for the delay, there were some technical issues going on, right? So people just let me know in the chats if I'm audible and visible to everyone. Hello Ishpreet, hi Shivam, hi Ashwarya, hello Bad, hi Dakshin, hi Prashant. Hello Fazan, hi Sujan, hi Aisha. Hello Karthi, hello Ashwarya, hello Akash, hi Yusuf. Welcome back everyone, welcome back. Just give me some green signal in the chats if I'm audible and visible to everyone people, right? Let me know fast in the chats. Let me know fast in the chats if I'm audible and visible to everyone. Good evening everyone, good evening. Welcome back, welcome back. Welcome back. I'm doing great Ashwarya, how are you? I'm doing good. Alright guys, so as you all must be knowing, in the last session we finished the hybridization and we talked about the dipole moment as well. We did some questions based on the dipole moment. I'm sure that's absolutely clear to everyone, right? People, in the tonight's session we are going to do one more theory in the chemical bonding, which is again one of the most important theories of the chapter, right? The name of the theory is VSEPR, valence shell electron pair repulsion theory, right? So before starting the session, the ones who are new to the channel, who have just joined in, let me introduce myself first. Well people, my name is Wassim Sir and I'm your chemistry master teacher right here on this NEET Elite channel, yeah? The ones who have not liked the video yet, please do like the video, share the video to your friends, do subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which I take live on this NEET Elite channel, yeah? Zahid, atomic structure is almost, it's done long back. You can check it in the videos. The chapter is done long back. Yes. Okay, so you can let me know in the chats if you people are super duper excited about the tonight's session as well, right? Let me know people, let me know fast in the chats if you guys are super duper excited. Right? Yes, Akash, molecular orbital theory will be done after this VSEPR, right? So tonight we are going to finish this valence shell electron pair repulsion theory, right? And after that, tomorrow I'm going to have a Menti session for you guys, right? Till VSEPR theory. And after that session, I mean day after tomorrow, we'll be doing the molecular orbital theory in detail, right? Yes, DGP Gamer, you can do that. This chapter will take, I guess, 4 more sessions, right? 4 more sessions for this. No, Ganesh, I'm not coming to Bangalore, bro. Rest all the teachers are in Bangalore, I know. I'm missing it. Yes, absolutely. Right? I could not go there. Anyways, let's get going. Let's get started with something called as valence shell electron pair repulsion theory, right? Okay. So, people, before starting this valence shell electron pair repulsion theory, if you remember, in the last session, we completed the hybridization, right? Well, hybridization, it used to give us the idea about the geometry of the molecule. I hope you remember that. Hybridization, it used to give us the idea about the geometry of the molecule, right? Let's say if any molecule, the hybridization involved is sp, we used to say the molecule has got the linear geometry, right? If in a molecule the hybridization involved used to be sp2, we used to say the molecule has trigonal planar geometry, right? Trigonal planar geometry. Similarly, if the hybridization involved in a molecule used to be sp3, right? We used to say the molecule has got the tetrahedral geometry. I hope you remember this. Similarly, if in a molecule the hybridization involved is going to be sp3d, we say the geometry of the molecule is going to be trigonal bipyramidal. Trigonal bipyramidal. Right? Similarly, if in a molecule the hybridization involved is sp3d2, we say the geometry involved in the molecule is going to be octahedral. And similarly, if in a molecule the hybridization involved is sp3d3, we say the geometry of the molecule is pentagonal bipyramidal, right? This is something which we have discussed till now in the last session, right? Yes? It's blur. People, is the screen blur? Is the screen blurred? Can you let me know in the chats? I think it's all okay. No, it's perfectly fine, right? So Ashi, you can just change the settings of the video, right? Just improve the quality of the video, it'll be fine for you, right? Or maybe you just refresh the page once. Yes, you guys just refresh the page once. The ones who are having the blur screen, yes, just refresh the page once, or you can just increase the quality of the video, it'll be fine, yeah? Okay, so people, this is something which we have discussed in the last session. Basically, hybridization used to give us the idea about the geometry of the molecule. If in any molecule the hybridization involved is sp, we used to say the molecule's geometry is going to be linear. Similarly, sp2, the geometry of the molecule is going to be trigonal planar, and so on. So basically, hybridization, it used to give me the idea about the geometry of the molecule, right? So what about this VSEPR? What about this VSEPR? VSEPR is going to give me the idea about the actual shape of the molecule, right? This theory is going to give me the idea, this is one of its benefits. This theory is going to give me the idea of the actual shape of the molecule, right? So let's get going then. Let's get started with valence shell electron pair repulsion theory, right? Let's get going. Have a look, guys. First of all, let me show you the main points of this theory, right? The first point, which is very, very, very important. This is very important. What is it? See, guys. Shape or geometry of the molecule is determined by the repulsions between the valence electrons of the central atom, right? What does that mean? Have a look exactly what is meant by all this. For example, I'm taking a molecule as NH3, right? Let's say this is the molecule which I'm taking over here, right? So people, if you remember, nitrogen, how many electrons it has got in the valence shell? It has got definitely 5 electrons in the valence shell. These are 2, 3, 4 and 5, right? These are the valence shell electrons of nitrogen, correct? Now out of these 5 valence electrons of nitrogen, only 3 electrons of nitrogen participate in the bonding, right? So this electron is going to make a bond with hydrogen, this one with one more hydrogen, this one with one more hydrogen, right? So nitrogen had basically 5 valence electrons, and out of 5 valence electrons, as you can see, only 3 valence electrons are participating in bonding, and those electrons which belong to the valence shell and participate in the bonding, those electrons are called as bonding electrons. So these 3 electrons I'll be calling as the bonding electrons, right? Whereas those electrons which actually belong to the valence shell but do not participate in the bonding, those are called as non-bonding electrons. So these 2 electrons I'm calling as non-bonding electrons. You can either call them as the non-bonding electrons, or you can call them as the lone pair electrons, right? You can call them as the lone pair electrons as well. The choice is all yours, right? So first thing, those electrons of the valence shell which participate in the bonding are called as the bonding electrons, whereas those electrons of the valence shell which do not participate in the bonding, those are what we call as the non-bonding electrons, or you call them as the lone pair electrons, right? Yes, as simple as that. Now people, as per VSEPR theory is concerned, the shape of the molecule or the geometry of the molecule is basically governed by, the repulsions, is basically determined or governed by the repulsions between the valence electrons of the central atom, right? So basically, these are the 5 valence electrons of nitrogen. Now there will be definitely repulsions between them, right? Those repulsions between the valence electrons are basically going to determine the shape of the molecule, right? And how come they are going to determine the shape of the molecule? That's something which we are going to discuss in detail, right? Okay, so remember one thing, the shape or geometry of the molecule is decided by the repulsions between the valence electrons of the central atom, you can say, right? As simple as that. Point number 1, which I'm sure you guys will be remembering from now onwards. Point number 2, right? Point number 2. Well, people, if I talk about the valence electrons, right? If I talk about the valence electrons, or if I talk about the valence electron pairs, right? Valence electron pairs. For example, if any atom has got some 6 valence electrons, that means it has got 3 valence electron pairs. If someone has got some 8 valence electrons, that means it has got some 4 valence electron pairs, right? Okay. What is the order of the repulsions between these valence electron pairs? Let me tell you, valence electron pairs are of 2 types. One is going to be called as the bonding electron pair, One is called as non-bonding electron pair, or you call them as the lone pair, correct? These valence electron pairs are basically of two types, you can say now. One is going to be the bonding electron pair, one is going to be the non-bonding electron pair, or you call them as the lone pairs, right? Now basically, there will be repulsions between these valence electron pairs, right? What is the order of those repulsions? Do remember, lone pair repulsions are always greater than the lone pair bond pair repulsions, which are again greater than the bond pair repulsions, right? This is the order of repulsions between these valence shell electron pairs, right? The repulsions between lone pairs and lone pairs are maximum, followed by lone pair, followed by bond pair. Do remember this thing as well, correct? Okay, so basically the shape of the molecule, the geometry of the molecule is decided by the repulsions between lone pairs, as well as lone pairs, bond pairs, as well as bond pairs and bond pairs, right? Okay, and do remember, the molecule is going to be acquiring that shape, that geometry. The molecule is going to acquire that shape, that geometry, in which the repulsions between these valence electron pairs will be minimum, because lesser the repulsions, more the stability. Lesser the repulsions, more the stability. Do remember this. Lesser the repulsions between these valence electron pairs, valence shell electron pairs, right? More is going to be the stability of the molecule. So the molecule is going to attain that shape, the molecule is going to attain that geometry in which the repulsions between these valence shell electron pairs will be minimum, right? Do remember this thing as well, right? Okay. Now people, this is something which I told you. This is the order of the repulsions, right? Now let's move on to the next point. Repulsions increase with the increase in the number of bonds. More the number of bonds, more are going to be the repulsions. Do remember this one as well. This is triple bond, this is double bond, this is single bond, right? Repulsions increase with the number of bonds as well. Repulsions increase with the increase in the bonds as well, right? This is a triple bond wherein maximum repulsions will be there, followed by double bond, followed by triple bond, right? What is the need of all this? You'll get the idea in some time only, right? I want you guys to copy all these statements first of all, then only I can talk exactly about the shapes and the geometries of the molecule. Yes? Moving on to one more thing. This is important. If a molecule contains only bond pairs, if the molecule contains only bond pair of electrons, if the molecule contains only bonding pair of electrons, then it is said to have the regular geometry as predicted through hybridization, right? See, I told you in the last session of hybridization. Hybridization gives us the idea about the geometry of the molecule. If I'll be having any molecule in which the central atom does not have any lone pair. Let's say I've got any molecule in which the central atom does not have any lone pair. Do remember, in that molecule, whatever is the expected geometry through hybridization, that is going to be the actual shape. So wherever in a molecule the central atom does not have any lone pair, the geometry which is expected as per hybridization is going to be the actual shape of the molecule. What is meant by that? Let's have a look. Let me give you one example. If you take the case of CH4, methane, all of you must be knowing, right? So you guys have a look exactly. This carbon, it has got some 4 valence electrons, right? As you all must be familiar with. It has got some 4 valence electrons, correct? Yes. And in CH4, this carbon is using all its 4 valence electrons to form 4 sigma bonds with hydrogen, right? Is there any lone pair on carbon? There is no lone pair on carbon, because carbon had 4 valence electrons and it has used all its 4 valence electrons for the 4 sigma bonds. So there is no lone pair on carbon, right? If there is no lone pair on the central atom, so whatever is going to be the expected geometry of this molecule through hybridization, that is going to be its actual shape, right? See, if I ask you how many sigma bonds this carbon is forming, you'll say carbon is forming 4 sigma bonds. If I'll ask you how many lone pairs are there on carbon, you'll say 0. If I'll ask you what about the steric number is sigma bonds plus lone pairs, 4 plus 0 comes out to be 4. If I ask you what is the hybridization, that's sp3. If I ask you as per hybridization what is the geometry, you'll say tetrahedral, right? You'll say tetrahedral, correct? Right? So this is the geometry of the molecule as per hybridization, correct? And in any molecule, if the central atom does not have any lone pair, whatever is the expected geometry through hybridization, that is going to be the actual shape. So actual shape as well as geometry of this CH4 is going to be tetrahedral, right? As simple as that. If I talk about PCl5, If I talk about PCl5, right? Okay, how many sigma bonds it's forming? It's forming 5 sigma bonds. Phosphorus, it belongs to group 15 elements, right? It belongs to group 15 elements. Group 15 elements, they have got 5 valence electrons. So this phosphorus has some 5 valence electrons, and it is using all the 5 valence electrons to form 5 sigma bonds with chlorine, right? So it is using all the 5 valence electrons to form 5 sigma bonds. So is there any lone pair on phosphorus? There is no lone pair on phosphorus. So if I ask you about the steric number is going to be sigma plus lone pair, that's 5. So what is going to be the hybridization of this molecule? Let's say sp3d, right? In case of sp3d hybridization, what is the expected geometry? You know it. It is trigonal bipyramidal, correct? See, is phosphorus having any kind of a lone pair? No, phosphorus does not have any kind of lone pair. The central atom does not have any kind of lone pair, right? And if in a molecule, the central atom does not have any kind of a lone pair, do remember, whatever is going to be the expected geometry through hybridization, that is going to be the actual shape, right? So I'll say the actual shape of this molecule as well as geometry of this molecule, both are going to be same, right? Yes, as simple as that. Perfect. Let's move on to one more point. If a molecule contains, or let me present it to you like this. If in a molecule, the central atom, it's forming, it's having bond pairs as well as lone pairs, right? Let's say I've got a molecule in which the central atom has got the bond pairs as well as lone pairs. Remember, in that molecule, the geometry which is expected through hybridization is not going to be the actual shape. Do remember this thing, right? Whenever I'll be having the molecule in which the central atom contains both bond pairs as well as lone pairs, right? Do remember, whatever is the expected geometry through hybridization, that won't be the actual shape of the molecule. Yes? Let me show it to you. If you talk about NH3, ammonia, right? If I talk about NH3, correct? I'm talking about NH3. Well, people, you all must be familiar with the fact nitrogen has got 1 lone pair, right? So first thing, how many sigma bonds are being formed? 3. How many lone pairs are there on nitrogen? 1. So 3 plus 1 comes out to be 4. Steric number is 4. And if the steric number is 4, the hybridization is sp3. If the hybridization is sp3, the geometry should be tetrahedral, right? The geometry should be tetrahedral. But have a look. Is the central atom having a lone pair? Absolutely. As I told you a few minutes back only, whenever the central atom contains bond pairs as well as lone pairs, its expected geometry through hybridization is not going to be same as of its shape, right? No doubt, it has got the tetrahedral geometry, but its shape is not going to be tetrahedral. What is its shape? Its shape is going to be like this. This is nitrogen, this is hydrogen, this is one more hydrogen, this is one more hydrogen, and there's a lone pair. It has got the pyramidal shape. It has got the pyramidal shape basically. It has got the pyramidal shape, correct? I'm going to show you all these shapes in some time. I'm simply making you understand few basic things first of all, right? It has got the pyramidal shape, yeah? Right, people? So do remember this as well. If a molecule contains both lone pairs and bond pairs, its geometry and shape will be different, right? I'm sure it's clear to everyone. Yes? Now, as I told you a few minutes back only, the molecule is going to be attaining that geometry, that shape, in which there will be less repulsions between lone pairs, bond pairs, as well as bond pairs, right? In short, that shape in which the repulsions between the valence electron pairs is minimum, that shape will be attained by the molecule exactly, right? Do remember this. The molecule acquires that shape in which the repulsions between different electron pairs is minimum, because lesser the repulsions means definitely more will be the stability. That's all. Lesser the repulsions, more the stability. As simple as that. Yes? Moving on. Before talking about the actual shapes of the molecules, before talking about the types of the molecules, let's have a glimpse on something called as bond angle as well. This valence shell electron pair repulsion theory, it's going to give me the idea about the bond angles as well, right? Have a look exactly what I'm going to talk about. I'm currently going to take 3 molecules. One I'm taking as CH4, one I'm taking as NH3, and one I'm taking as H2O. These are 3 molecules which I'm taking, right? Because I need to make you understand few important things, right? I took these 3 molecules, CH4, NH3 and H2O, correct? Have a look exactly. See guys, this is C, this is H, this is one more H, this is one more H, and this is one more H, correct? This is CH4. If you talk about NH3, nitrogen, it's forming 3 sigma bonds, and at the same time, this nitrogen has got 1 lone pair as well. right? When we calculate, because in the last session only I've shown you how to calculate the lone pairs and bond pairs of the central atom, right? That's something which is understood, I believe, right? And if I talk about water, in water there are 2 lone pairs on oxygen, right? You can check it out as well, because we have seen how to calculate lone pairs and bond pairs of the formed by the central atom, right? Okay, now have a look. See guys, in this molecule, this carbon is forming 4 sigma bonds. There is no lone pair. Steric number is 4, so its hybridization is sp3, right? Over here, this nitrogen, 3 sigma bonds, 1 lone pair. 3 sigma bonds, 1 lone pair. Steric number 4, again its hybridization is sp3. What about this water? 2 sigma bonds, 2 lone pairs. Steric number 4, again its hybridization is sp3, right? Hybridization of all these central atoms is same, sp3. So the geometry of this molecule must be what? It must be tetrahedral. The geometry of this molecule, expected geometry of this molecule is tetrahedral. What about this one? It's also tetrahedral, right? Yes. And in case of tetrahedral geometry, you guys must be knowing the bond angle is 109 degree, 28 minutes. So bond angle over here should be how much? It should be 109 degree, 28 minutes. And in the second case also, it should be 109 degree, 28 minutes. Why is that? Because the hybridization is sp3, right? We have studied in sp3 hybridization, the bond angle is going to be 109 degree, 28 minutes. Similarly, in this case, the bond angle should be 109 degree, 28 minutes, correct? This is the expected bond order. This is the expected bond. Bond angle, sorry. I'm talking about the bond angle, okay? Yes. So the bond angle in all the 3 cases should be the same because the hybridization involved is same, correct? But what happens exactly? The bond angle in case of NH3 is not 109. The actual bond angle in case of NH3 is basically 107 degree, right? The actual bond angle in water is actually 104 degree 5 minutes. Why is that? Why is that? But in case of CH4, the bond angle is 109 degree 28 minutes only, right? Why is that? Why in case of NH3, the bond angle is slightly less than that of your 109 degree 20 minutes? Why in case of water, the bond angle is again less? What is the reason? Reason is the repulsions, either between lone pairs, or between lone pairs, or between bond pairs, right? See, if you talk about this CH4, everywhere you can see only single type of repulsions between bond pair and bond pair, bond pair and bond pair, bond pair, right? Everywhere you are seeing only single type of repulsions between bond pairs, right? But over here, if you take the NH3 molecule, we have got 2 types of repulsions. First, between bond pairs. Second, lone pairs, bond pairs, right? And the magnitude of repulsion between lone pair and bond pair is greater than the magnitude of repulsion between bond pair and bond pair, right? So can I say there'll be repulsions between this and this, there'll be repulsions between this and this, due to which these lines, these bonds, they are going to bend towards each other, due to which the bond angle is going to get reduced from 109 degree 28 minutes to 107 degree. As simple as that, right? Similarly, in case of water, you have got 2 lone pairs. So I must say the repulsions between lone pairs and bond pairs over here will be more, due to which the bond angle would have slightly got reduced more, correct? Yes, because we have got 2 bond pairs over here, right? So I can clearly say the bond angle in this case is going to be the minimum among the 3, right? So can I simply generalize the statement? More the repulsions, lesser the bond angle, as simple as that. Yes. Right? More the repulsions, lesser the bond angle. Correct? So I can say bond angle is simply inversely proportional to repulsions. More the repulsions, lesser the bond angle, as simple as that. Yes? Right? Okay, these are the 3 molecules which I've talked about. Correct? Now comes few more interesting things. There are few things which you must remember. Okay. What is the effect of electronegativity on the bond angle? Right? What is the effect of electronegativity on the bond angle? Well, people, let me tell you, this is the first case in which the central atom is different, right? If you talk about these 3 molecules, in these 3 molecules, the central atom is different. Over here, the central atom is nitrogen. Right here, phosphorus. Right here, arsenic. Right? And nitrogen, phosphorus, and arsenic, they belong to the same group. And on moving from top to bottom, what happens to electronegativity? Electronegativity decreases. That's something which is understood, right? Okay. Now, remember, when will be having certain molecules which will be having same hybridization, they have got same hybridization first of all. They have got same hybridization. This sp3, this is sp3, this is sp3. Hybridization is same. Now, terminal atoms are also same. 3 hydrogens, 3 hydrogens, 3 hydrogens. Only thing that is changing, that is the central atom, right? That is the central atom. Yes? Now, depending on the electronegativity of this central atom, you are going to decide the bond angles. Do remember, bond angle is directly proportional to electronegativity of the central atom. More the electronegativity of the central atom, do remember, more is going to be the bond angle, right? You can remember it like this. You can remember it like this. See how you need to remember it, okay? Just for the sake of remembering things. This is NH3, right? There is a lone pair on this nitrogen as well, correct? This is PH3. Just for the sake of remembering things, right? This is lone pair on phosphorus. This is arsenic, right? This is hydrogen, this is hydrogen, this is hydrogen, correct? Have a look exactly. Nitrogen being more electronegative compared to phosphorus, compared to arsenic, right? So nitrogen will be having more tendency to attract this bonded pair of electron towards itself, right? Among all. So I'll say all these three bonded pair of electrons will be very close to nitrogen. All these three bonded pair of electrons will be very close to nitrogen compared to this phosphorus, in which they'll be slightly far than that of earlier case, right? And over here they'll be little more far, I can say. They'll be little more far, right? Can I say in the first case, these bond pairs are the most, these are the closest, right? The distance between them is the least in the first case. In the first case, the distance between these bond pairs is least. Lesser the distance between the bond pairs, I'll say more will be the repulsions. And due to more repulsions, I'll say it's going to stretch. Yes, I'll say it's going to stretch, correct? Yes, if I ask you among all these three, wherein you see the bond angle to be maximum. Wherein you see the bond angle to be maximum. Wherever the electronegativity of the central atom is more, their only bond angle is going to be maximum. So this is the expected bond angle, right? Okay? Because the repulsions over here are going to be more, due to which the bond angle is going to get increased a bit, yeah? Yes, as simple as that. Yes, Akhil, I'm done with the overlapping. You can check it out. Right, people? I'm sure it's clear to everyone. Similarly, there is one more case when the central atom is same. When the central atom is same, but the terminal atoms are different. In this case, bond angle is inversely proportional to the electronegativity of the terminal atom. In this case, bond angle is inversely proportional to the electronegativity of the terminal atom, right? Okay. For the sake of remembering things, let me just tell you how to remember it, okay? See, if you talk about NF3, right? This is fluorine, and this is fluorine, correct? Similarly, if you talk about NCl3, this is Cl, and this is Cl, correct? If you talk about NBr3, this is, for example, Br, this is one more Br, and this is one more Br, correct? Right? Now, people, fluorine being the most electronegative among all these elements, right? Among all these terminal atoms, fluorine being the most electronegative. So, if fluorine is more electronegative, fluorine will be having more tendency to attract the bonded pair of electron towards itself. So, let's assume the bond pair is somewhere here. Let's assume this bond pair is somewhere here. Let's assume this bond pair is somewhere here, right? But in this case, whatever is going to be the distance between the center of the nitrogen towards this bond pair, the distance between nitrogen and this bond pair is not going to be the same, right? I'll say this bond pair will be comparatively closer to this nitrogen. The bond pair will be comparatively closer to the nitrogen. And in this case, the bond pair is going to be closest to the nitrogen. The bond pair is going to be closest to the nitrogen, right? So where do you see bond pairs are close? Where do you see bond pairs are close? I'll say bond pairs are close in this case. If bond pairs are close, I'll say repulsions will be more in this case. Right? Repulsions will be more in this case. If repulsions are more in this case, I'll say stretching of bonds will be more in this case, right? Stretching of bond angle will be more in this case, right? So in this one, the bond angle is going to be maximum, right? So this is going to be the expected bond order, right? So in short, do remember, bond angle is inversely proportional to electronegativity of the terminal atom. Less the electronegativity of the terminal atom, more is going to be the bond angle, right? See, everywhere hybridization is same, everywhere central atom is same, it is just the terminal atoms are changing. It is just the terminal atoms are changing, right? Wherever you see the electronegativity of terminal atom less, there only bond angle you are going to see more, right? Okay, this was about the bond angle, correct? Now let's move on to the actual application of the VSEPR. First of all, you can let me know in the chats if every single thing is clear till here, so that I can move on and talk about a few more important things. Let me know in the chats. Yes, let me know in the charts. Give me some green signal from the charts so that I'll move on and talk about the actual shapes of the molecules through VSEPR, yeah? How many more sessions? For this chapter, I'll be taking 4 more sessions, people, right? Okay. So tomorrow, basically, I'm doing the Menti session. Do join that. Day after tomorrow, it's going to be molecular orbital theory. There'll be one more session in which I'll be doing all the missing topics from this chapter, right? Like Fajan's rules, I've not discussed yet, right? There are some bond parameters as well, which I did not discuss yet. Hydrogen bonding is there, right? And in the session after that, I'll be doing all the previous equations from the chapter, right? And then you can let me know, right? You can let me know in the comment box of this video only which chapter do you want the next. If you want chemical equilibrium, ionic equilibrium, thermodynamics, GOC, whatever you want to, right, take, you can let me know in the comment section once the video ends, yeah? Hello Anjali, welcome. All right guys, so let's have a look on the actual application of this VSEPR, right? This VSEPR is going to give me the idea about the shapes of the molecules, right? First of all, I'm going to talk about those molecules in which hybridization involved is sp2. Let me talk about those molecules in which the hybridization involved is sp2. If the hybridization involved is sp2, what is going to be the geometry of the molecule? The geometry of the molecule is going to be what? Trigonal planar. Trigonal planar. This is something which is understood. This is something which we have discussed as well. Any molecule in which the hybridization involved is basically sp2, we say the molecule is going to show the trigonal planar geometry, right? Yes, absolutely. Now people, let's see all the molecules which come under this category. Let's see all the molecules which come under this category, right? See guys, first of all, when can be the hybridization sp2? Hybridization can be sp2 if steric number, hybridization can be sp2 if steric number is going to be 3, right? Now what is steric number all about? Steric number is nothing that is sigma bonds plus lone pairs, right? Sigma bonds plus lone pairs. Okay? Yes? So first of all, let me talk about those molecules in which, the sigma bonds are 3, or let me write it like this, in which the bond pairs are 3 and lone pairs are 0, right? What about the steric number of that molecule in which the central atom is going to show 3 bond pairs, it's going to form 3 bonds, right? And lone pairs are 0. What about the steric number of that molecule? Steric number of that molecule is 3. If steric number is 3, the geometry is going to be what? Or the hybridization is going to be sp2, the geometry is going to be what? The geometry is going to be trigonal planar, correct? Geometry is going to be trigonal planar, correct? Few minutes back only I told you. Whenever you see any molecule in which the central atom does not contain any lone pair, whatever is the geometry expected through hybridization, same is going to be the shape, right? So I'll say the shape of the molecule is also going to be trigonal planar. Yes? Shape of the molecule is also going to be trigonal planar. So this is the geometry as well as the shape of the molecule, correct? Because the central atom does not have any lone pair, right? And I'm going to represent this molecule like this, AB3L0, where A represents the central atom. It is forming 3 bond pairs, it is forming 3 bonds, and there is no lone pair on the central atom, right? The molecule is of the type AB3L0, correct? Right? Now people, AB3L0, no lone pair on the central atom. So whatever is the expected geometry through hybridization, same is going to be the shape, yeah? Okay, now have a look. This is the central atom A, this is your B over here, this is one more B over here, this is one more B over here. This is the scenario when the repulsions between the bond pair of electrons, between the bonding pair of electrons is minimum among all the things which you would have experienced. I mean, which you would have checked, right? This is the geometry, this is the shape of the molecule in which the repulsions are minimum, right? Because I've kept all these bonded pair of electrons at maximum distance apart, so that repulsions between them will be least and stability will be maximum, right? So this kind of a geometry, this kind of a shape is something which I call as trigonal planar shape. All these bonds, all these 3 bonds, they are going to be present on the plane, right? If this board is the plane, all these 3 bonds between A and B, they are going to be present on the plane, right? What about the bond angle? What about the bond angle? Bond angle is absolutely going to be 120 degree, right? I'm sure it's clear to everyone. Yes? Right? Absolutely, people. I'm sure it's clear to everyone. Yes? Now, in this sp2 category only, let's take a molecule in which The central atom is forming 2 bond pairs, right? And there is a lone pair present on the central atom. So 2 bond pairs, 1 lone pair. So steric number comes out to be again 3. If the steric number is 3, hybridization is again going to be sp2. If the hybridization is sp2, the geometry is going to be trigonal planar. Geometry I'm talking. Geometry is trigonal planar. If the geometry is trigonal planar, what about the shape? Is the actual shape going to be trigonal planar? No way. Why? Because the central atom has got the lone pair. Yes, the central atom has got the lone pair. Yeah? First of all, what is the type of the molecule? It's going to be like this. A, which is central atom, B2L1. A is the central atom, forming 2 bond pairs, right? Having 2 bond pairs, forming 2 bonds, correct? And there's a 1 lone pair on the central atom as well, correct? So its geometry, no doubt, its geometry is same, trigonal planar, right? But what about its actual shape? Let me show you its actual shape. So first of all, make its geometry. It is supposed to be like this. Right? But from this geometry, just remove one of the bond pair and put a lone pair instead of it, right? Okay, now just ignore this lone pair. What kind of shape is it? Just ignore this lone pair. What kind of shape is it? Can you say it's a simple bent shape? Absolutely, it's a bent shape. So the shape of the molecule is bent, right? Or you call it as a V shape, or you call it as the angular shape, right? Yes? You call it as bent shape, angular shape, whatever you want to call it, you can do that. So geometry of this molecule is absolutely trigonal planar, but the shape is actually bent, right? This was the first category of the molecules in which the hybridization of the central atom involved is sp2, right? Now, the second category of the molecules in which the hybridization involved is going to be sp3. If hybridization involved is sp3, right? What about the geometry of the molecule? I must say, geometry of the molecule is going to be tetrahedral. And if the geometry of the molecule is tetrahedral, right? What about the steric number? See, for sp3 hybridization, I'll say steric number is equal to 4, right? Steric number, which is basically sigma plus lone pairs, this is equal to 4. Correct? This is something which is understood. This is something which we have seen already, right? Yes. Now we will have a look exactly what I'm going to talk about. In this sp3 hybridization, let's see all the cases which arise over here. Let's take all the cases which arise over here. The first case which arises over here. If the bond pairs are going to be 4, lone pairs will be 0. If in a molecule, the central atom is forming 4 bond pairs and 0 lone pair on it, right? Again, the steric number is going to be 4 plus 0, right? Steric number is going to be 4 plus 0, that is 4. If the steric number is 4, the hybridization is sp3. If hybridization is sp3, what is the geometry? Geometry is tetrahedral. But is the shape going to be tetrahedral? Absolutely, the shape is going to be tetrahedral as well, because the central atom does not have any lone pair, right? This molecule is of the type AB4L0, right? A is the central atom, 4 bond pairs and 0 lone pair on the central atom. So shape and geometry both are going to be same, right? And how does it look like? See, this is A, for example. This is B over here. This is one more B. This is one more B which is behind the plane. This is one more B over here. It looks like a tetrahedral shape. Right? It looks like a tetrahedral shape like this. It looks like a tetrahedral. Well, I could not make it properly, but it's understood, right? It looks like a tetrahedral shape. Yeah? Now, if it is tetrahedral, what is going to be the bond angle? It's absolutely going to be 109 degree 28 minutes, right? So the molecule which is of the type AB4, it is absolutely going to have the same geometry and the shape, and both are going to be what? Tetrahedral, right? Yes? Right? Someone is saying, sir, use white color. You want me to use the white color? Is that? Is that? Okay, I'll be using the white color after this sp3 hybridization. Okay, let's cover all the cases first. Then I'll change the. Currently, I'm using Android system, and after that, I'll be using Node. Right? Just wait for it. Okay. Now let's move on, people. Let's talk about the molecule in which the central atom is forming 3 bond pairs and there is 1 lone pair, right? 3 bond pairs, 1 lone pair. What about the steric number? Steric number is again 4. If steric number is 4, the hybridization is sp3. If the hybridization is sp3, the geometry is going to be tetrahedral. But what about the shape? Shape is not going to be tetrahedral, right? Shape is not going to be tetrahedral because the central atom is containing a lone pair. What is going to be the type of the molecule? It's absolutely going to be AB3L1. It's absolutely going to be AB3L1, right? Yes, so let me represent it for you. Let me show it to you. Let me show it to you. This is A, right? This is B. This is one more B. This is one more B. And there's a lone pair over here, right? They are forming a pyramid kind of a thing. They are forming a pyramid kind of a thing, right? This is the actual shape. Pyramidal shape, right? The actual shape is going to be pyramid. The geometry is absolutely going to be tetrahedral, but the actual shape is going to be pyramidal, right? Yes? Now similarly, guys, there is one more case in which the bond pairs are 2, lone pairs are 2. Bond pairs 2, lone pairs 2. Steric number 4. If steric number is 4, hybridization sp3. Hybridization sp3, geometry tetrahedral. But what about the shape? What about the type first of all? Type is going to be AB2L2, right? 2 bond pairs, 2 lone pairs, correct? What about the shape now? See, the geometry is no doubt going to be tetrahedral, but is the shape going to be tetrahedral? No, no way, right? No, no way. Why? Why is that? Because the central atom has got 2 lone pairs, right? So what about the actual shape? It's going to be like this. This is A, this is A, this is one bond pair, this is one more bond pair, this is a lone pair over here, this is a lone pair over here, right? It's again a bent shape. The shape of this molecule of the type AB2, L2, it's going to be bent. Like in case of water. I'm going to give examples in some time, right? This was all about what? sp3 hybridization, right? So, just a second. Let me change the color and everything. Let me use some other things, which I've never tried, basically. But let's try it out. Let's try it out. Let's use note. Just a second. Yeah, this is perfect, yeah? Right? It's perfect, I believe. Okay? Perfect, guys. Let's move on. Let's move on. Till now, we talked till sp3 hybridization, right? Yes? Now, it's going to be the time for the molecule in which the hybridization involved is sp3, right? Sorry, sp3d. Correct? In the molecule which involves sp3d hybridization, what is going to be the steric number first of all? Steric number is going to be sigma plus lone pairs, right? Sigma plus lone pairs. And the value comes out to be how much? The value comes out to be 5. Steric number, value comes out to be 5, right? What about the geometry? The geometry of the molecule is going to be, it is going to be trigonal bipyramidal. It's going to be trigonal bipyramidal, right? Just a second, people. Yeah, now it's fine. Okay, the geometry of the molecule is going to be what? Trigonal bipyramidal, correct? Now have a look exactly what all molecules come under this category. Let me exactly show you what all molecules come under this category. Have a look. The first molecule in which there will be 5 bond pairs formed by the central atom and there is no lone pair on the central atom. 5 bond pairs, no lone pair. What about the steric number? Steric number is going to be 5 plus 0. That comes out to be 5. If steric number is 5, the geometry is going to be what? Trigonal bipyramidal. And people, we know in the molecule, if the central atom does not have any lone pair, shape is geometry, right? So its geometry as well as shape, both are same. And how am I going to show it? First of all, the type of the molecule is going to be A. Oh my God, just a second, people. The type of the molecule is going to be A, B5L0, right? A, B5L0. A is the central atom, 5 bond pairs, 0 lone pair, right? How do we make it? This is A over here, right? This is, for example, 1 of the B, this is 1 of the B, and this is 1 of the B, correct? Right? These 3 bonds over here, they are present on the same plane. These 3 bonds over here, they are present on the same plane. Now, there'll be 1 bond perpendicular to the plane. There'll be 1 more bond perpendicular to the plane like this, right? Okay. So basically, this AB bond, this AB bond, this AB bond, they are present on the same plane. There is 1 bond perpendicular upwards, 1 bond perpendicular downwards, right? If you just join the things like this, if you join these atoms like this, if you join the atoms like this, the shape is going to be what? It's going to be what? It's going to be called as trigonal bipyramidal, right? This molecule has got the shape of what? it has got the shape as well as geometry of trigonal bipyramidal, right? Now people, remember, these bonds which are perpendicular to the plane, I mean this bond and this bond, these are what we call as axial bonds. I hope you remember the last session, I've discussed this. These are what I call as axial bonds. And what about these three bonds? These are what I call as equatorial bonds. And I have discussed already the axial bond length in case of trigonal bipyramidal geometry is always greater than the equatorial bond length. This is something which is discussed already, right? This is something which is discussed already. Yeah? I'm sure it's clear to everyone, right? Let's move on. Let's move on to one more category. The next category, in which you'll be finding some 4 bond pairs, 1 lone pair. 4 bond pair, 1 lone pair. Steric number again 5. If the steric number is 5, the geometry is again trigonal bipyramidal. What about the type of the molecule? Now it's going to be AB4L1, right? Now it's going to be AB4L1. Okay. Now again, the geometry indeed is going to be trigonal bipyramidal, but what about the shape? What about the shape? Shape is not going to be trigonal bipyramidal. Shape is going to be something called as seesaw, right? Shape is going to be seesaw. Let me show you exactly what the seesaw shape is all about, right? See, this is A over here, for example. This is one of B. This is one more B, right? Over here, at the equatorial position, there's a lone pair, right? At the equatorial position, there's a lone pair. There is one bond perpendicular like this. There is one more bond perpendicular like this, right? Just ignore the lone pair, then see it. Just ignore the lone pair, then see it. You'll find it like a seesaw, right? This shape is what we call a seesaw shape. So any molecule which is of the type AB4L1 is definitely going to have seesaw shape, right? I'm sure it's clear. Similarly, the next category, which falls into sp3d, if the bond pairs are 3, but lone pairs are 2. Bond pairs 3, lone pairs 2. Steric number again going to be 5, right? The geometry again going to be trigonal bipyramidal. If the geometry is trigonal bipyramidal, what about the type of the molecule? It's going to be AB3L2, right? In which A is the central atom, 3 bond pairs, right? And 2 lone pairs, correct? How do we draw this? First of all, is its geometry going to be its shape? No way, because the central atom has got 2 lone pairs, right? Yes. So what about its shape, people? Can you let me know its shape? Can you let me know about its shape? See guys, how its shape is going to be. This is A, right? This is, for example, one lone pair at the equatorial position, one more lone pair at the equatorial position. This is a bond pair on the same plane in the equatorial plane, right? Now, there is one more B over here perpendicular, one more B over here perpendicular. If you want to have a look on the shape, just ignore these 2 lone pairs, then see the molecule. It's going to be a T-shaped. It's going to be a T-shaped, right? It's a T-shaped molecule. So any molecule which is of the type AB3L2 is going to be having the trigonal bipyramidal geometry, but the shape is going to be T. Yes? Absolutely. Let's have a look on the other molecules as well. So first of all, I need to erase all this. Correct? So the fourth one, in which you'll be having 2 bond pairs and 3 lone pairs. 2 bond pairs, 3 lone pairs. Again, steric number is 5. Again, the geometry is trigonal bipyramidal. The type is now going to be AB2L3. AB2L3, right? AB2L3. Is its geometry going to be its shape? No way, right? Its actual shape is going to be like this. This is, for example, A. There are 3 lone pairs which are basically present on the equatorial plane. On equatorial plane, this is the equatorial plane which I'm talking about, right? There is one bond pair in this way perpendicular to this plane, one bond pair like this perpendicular to the plane. Now ignore these lone pairs and see the molecule. The molecule is going to be linear. The molecule is going to be linear. So any molecule of the type AB2L3 is going to be linear. Its shape is going to be linear, but its geometry is going to be what? Trigonal bipyramidal. So with this, your sp3d hybridization molecules are over, right? Now let's have a look on the next category, which is sp3d2. Then we can solve some questions as well, right? So let me erase all this. Let me erase all this. Now have a look exactly on the category of sp3d2. Molecules in which the hybridization involved is sp3d2. They have got the steric number, which is basically sigma plus lone pairs, right? They have got the steric number of 6, right? Steric number of 6, and the geometry is basically going to be what? The geometry is going to be octahedral. I hope you remember it. The geometry is octahedral. This is something which is known, correct? Now in these molecules in which the hybridization involved is sp3d2, the first category is of the type AB6L0. AB6L0. This is of the first type. AB6L0, correct? Right? This is the first type. Or let me not write this AB6L0, let me write it in our way, the way we used to write it till now, right? See guys, First of all, let's say I've got the molecule in which the central atom is forming some 6 sigma bonds and there is no lone pair on the central atom. So what about the steric number? Steric number is going to be 6 plus 0, that is 6. If the steric number is 6, the hybridization involved is sp3d2, right? If the hybridization involved is sp3d2, the geometry is going to be octahedral, right? Since the central atom does not have any lone pair, so whatever is going to be its geometry, same is going to be its shape as well, right? Same geometry, yes, same shape. So how it is made? This is A, for example, the central atom. This is B. This is one more B. This is, for example, one more B. And this is one more B. All these 4 bonds, they are present on the same plane. All these 4 bonds, they are present on the same plane. They are basically present on the equatorial plane. There is one bond perpendicular to the plane like this upwards. One bond perpendicular to the plane like this downwards. Now, if you join them, you are going to get the shape as, right? You are going to get the shape as octahedral, correct? This is what you call as octahedral shape. And this is something which we have discussed in hybridization as well, right? This is what you call as octahedral shape. Yes? Right? I'm going to give you the examples in some time. Yeah? Now, moving on to the next category of this, in which we have got some, I did not mention the type of the molecule, it's going to be what? It's going to be AB6L0, correct? Now, moving on to one more, in which you'll be having 5 sigma bonds and there is one lone pair. 5 sigma bonds, one lone pair, right? Steric number comes out to be 5 plus 1, 6. If steric number is 6, again it's going to be sp3d2. Again, the geometry is octahedral. But what about the shape? Is the shape going to be octahedral now? Now the shape is not going to be octahedral. What is the shape going to be? This is A. These are the 4 bonds which are present on the same plane, right? Which are present on the same plane basically. Okay, there is a lone pair perpendicular to the plane like this, right? And there is a bond pair over here like this, correct? This shape is basically, just ignore the lone pair and see it. Just ignore the lone pair and see the molecule. So over here in this one, you were seeing some 2 pyramids, right? You are seeing some 2 pyramids, and over here you are seeing only 1 pyramid downwards. Or it can be 1 pyramid upwards in which the lone pair will be downwards, right? So this shape is called as square pyramidal shape. This is what I call a square pyramidal shape, yeah? Right? I'm sure it's clear. Similarly, talking about few more molecules, but before that, let me erase this part. Okay. Let's say I've got the next type of the molecule in which the sigma bonds are 4, lone pairs are 0. 4 sigma bonds, 2 lone pairs, steric number same, hybridization same, geometry same. Now, what about the type of the molecule? The type of the molecule is AB4L2. What was the type of the molecule of this type? It was AB5L1, right? It was AB5L1, correct? What about the shape of AB4L2? It is something which we call a square planar shape, right? This is A, this is B, this is one more B over here, right? Everywhere you have got BB, correct? Now if you join them like this, right? There's a lone pair over here, there's a lone pair over here. Now you can see only one plane which is basically square in shape. It's a square planar shape, right? It's square planar shape. AB4L2 type, right? Similarly, if I talk about the next one, in which you'll be having 3 sigma bonds and 3 lone pairs, AB3L3 type, right? Steric number 6, geometry same, hybridization same, everything same, but the type of the molecule is different now. It's going to be AB3L3, AB3L3, correct? What about the shape of this molecule? Can you let me know? Can you let me know, people? AB3L3. Can you let me know fast? Can you let me know what is going to be the shape? Waiting for your answers. There is no molecule as such in which this category is fulfilled, right? Okay? Yeah? Let's move on. Let's move on. Let's move on to now comes the case of what? sp3d3, right? This is the last category. sp3d3. sp3d3. What about the steric number here? Steric number, which is basically sigma plus lone pair. Steric number over here is 3, 3, 6, 1, 7. Correct? Steric number is 7, and the geometry is going to be pentagonal bipyramidal. Pentagonal bipyramidal, correct? Yes? Now have a look exactly. The first type over here, right? And the only type which I'll be showing over here, that is the one in which you'll be having how many bond pairs? you'll be having some 7 bond pairs and 0 lone pair on the central atom. The type of the molecule is going to be AB7L0, in which geometry as well as shape both are going to be same because the central atom does not have any lone pair, right? How do we represent it? This is A, right? And you have got 7B. This is 1, 2, 3, 4, 5. Correct? So have a look exactly how it's going to get formed. Just a second, guys. These are basically the bonds. These are the bonds. Dotted lines are not the bonds. Solid lines are the bonds, right? So all these 5 bonds, they are present on the same plane, right? There is 1B perpendicular upwards, 1B perpendicular downwards, right? Now, if you join the axial atoms with the equatorial atoms, you'll be getting something called as pentagonal bipyramidal shape, right? I'm sure every single thing is clear till here, right? Now, I'll be taking certain molecules, and by having a look on those molecules, all this is going to get clear to you, right? Yes? Okay, now let's have a look on the molecules by means of which you can decide every single thing. See guys, this is something which we have discussed, every single thing we have discussed, and you are going to get this PDF in the Telegram group as well. Yes? Right? Okay. Alright, application of VSEPR theory, right? Oh, did I miss AB6L1? Did I miss AB6L1? Walaikum salam Ikra. Okay, this is AB6L1 people. This is AB6L1 in which you have got distorted octahedral shape, right? This is distorted octahedral, right? Have a look on this. This is what we call as distorted octahedral, and this is a lone pair over here, right? This lone pair is basically not present on the equatorial plane. This is slightly above it, right? You can say. It's not present on basically the equatorial plane, right? This AB6L1 distorted octahedral you call it, yeah? Anyways, let's have a look on these molecules. Let's talk about their geometry, their shape, everything, right? So first of all, BeCl2. BeCl2. How many valence electrons are there with beryllium? There are 2 valence electrons with beryllium, central atom. How many sigma bonds it's forming? The number of terminal atoms, that is 2 sigma bonds. So it had some 2 valence electrons, and both the valence electrons it's using to form 2 sigma bonds, so there is no lone pair on beryllium. If there is no lone pair on beryllium, what about steric number? Steric number is 2, right? What about the geometry? The geometry is going to be linear. The geometry is going to be linear. Since there is no lone pair on the central atom, so whatever is the geometry, that is going to be the shape as well. Shape as well as geometry linear, right? Yes? Okay, NH3. NH3. Now you know how to calculate the sigma and lone pairs, right? I'm just going to write it now. Sigma bonds 3, lone pair 1. Sigma bond 3, lone pair 1. What is the type of the molecule? AB3L1. AB3L1. What is the steric number? 3 plus 1, that is 4. Steric number is 4. Hybridization, that is sp3. If hybridization is sp3, geometry, that is tetrahedral. Shape is going to be pyramidal, right? AB3L1 molecule has got the shape pyramidal, correct? Yes? Right, people? Similarly, NH4 positive. So there are 4 sigma bonds. There is no lone pair on the central atom. The hybridization is sp3. The geometry of the molecule is AB4L0. If it is AB4L0, no lone pair on the central atom. So whatever is going to be this geometry, same is going to be this shape. So geometry and shape both are same, tetrahedral. Right? Similarly, if you talk about SF4, there are some 4 sigma bonds. There is 1 lone pair on sulfur, right? Steric number is 5. If steric number is 4 plus 1, 5, the hybridization is sp3d. If hybridization is sp3, which d orbital is involved in hybridization? It is dz square, right? What is the type of the molecule? The type of the molecule is AB4L1. What is the geometry of the molecule? Geometry of the molecule is trigonal bipyramidal. What about the shape of the molecule? That is seesaw, right? Every single thing you can do. Every single thing you can do. Okay? Talking about few more examples. These are few more examples. Well, if you talk about carbon dioxide, right? This is carbon dioxide, people, as you all must be knowing. So how many valence electrons on carbon? There are 4 valence electrons, right? So let me make it for you. So how many sigma bonds first of all? There are 2 sigma bonds, right? There are not 4 sigma bonds, 2 sigma bonds. Is there any lone pair on carbon? There is no lone pair on carbon. So steric number is 2 plus 0, that is 2, right? So hybridization is sp, right? Central atom does not have any lone pair. So whatever is going to be the geometry, same is going to be the shape, linear, both, right? XCF4, 4 sigma bonds, lone pair on xenon 2, steric number 4 plus 2, 6, hybridization is sp3d2, right? Geometry of the molecule is octahedral. Shape of the molecule is what? Square plane. All these things you can talk about. Yes? I3 negative. I3 negative. It is of the type AB2L1. Or see guys, you can write this I3 negative in this way as well. You can write it as I2 negative. You can write it as I2 negative. Let's call this iodine as the central atom A. So it's going to be B2, right? AB2. Is there any lone pair on this iodine? Have a look. Iodine has got some 7 valence electrons, but 7 plus 1, 8. Out of 8, it is using 2. So there are 6 electrons left as such on this iodine. So 6 electrons means 3 lone pairs. So 3 lone pairs, AB2L3 type. Steric number is going to be what? Steric number is going to be 3 plus 2, 5. Hybridization is going to be sp3d. If hybridization is sp3d, the geometry is going to be trigonal bipyramidal. Geometry is trigonal bipyramidal, but its shape is going to be linear, right? Yes, we have discussed this in detail, right? Now I'm going to give you a few examples and you are going to, okay, I did not give you any example as the homework. So should I be giving you some examples as the homework? Okay, I'm giving you certain examples as the homework. Do let me know the shape and geometry of SO2. Do let me know the shape and the geometry of XeOF4, right? Do let me know about this as well, XeO2F2. Right? Okay, do let me know about their shapes and geometries in the comment section, right? So with this people, your valence shell electron pair repulsion theory is done and dusted, right? And the ones who have not enrolled into the actual Vedantu platform yet, do get enrolled in the actual Vedantu platform as soon as possible because the next batch is starting soon, right? Do get enrolled. The link is there in the description box of the video, yes? And people, do let me know in the comment section which chapter you want the next, right? So that I can start making slides for those, okay? For that chapter, I mean. Anyways, the ones who have not liked the video yet, please do like the video, share the video to your friends, and do not forget to subscribe to the channel as well. The ones who are preparing for NEET 2023, well, people, we have got 3 plans for you. If you want to be with us on the actual Vedantu platform, if you want to get trained by us in all the 3 subjects for the complete 2 years, from now onwards, you need to take any of the pro subscription, right? All these pro subscriptions, these are basically 2-year classroom programs, right? The first one is light program. What all benefits you get in this one? You get live interactive online classes with the teachers of your choice, test series analysis, notes, study material. Study material is one of the best study materials, guys. Trust me on that. Yes, and at the same time, if you are new to Vedantu, you have no idea how the actual Vedantu platform looks like, you can take this subscription for a month, right? If you think you are getting benefited, then go for the actual one, 2-year one. And trust me, people, you are going to love it, right? Get enrolled and through this or this or this, right? Through 1 month pro subscription, then you're going to get to know that what is the actual Vedantu platform all about, right? And trust me, you are going to love it. Yes, and this is the complete course fee for 2 years if you are choosing this light program, and no need to pay this much of amount in one go. You can pay this much of amount in installments as well. No issues at all, right? Okay, so do like the video, share the video, and subscribe to the channel. So let me show you exactly how to get enrolled in this one. This is the video which you guys are currently watching. You need to drag this video a little down, click on this, show more. After clicking on this, show more, you'll be getting a lot of links over here. So the majority of the students currently are looking for CBSE Term 1 crash course, right? If you are also looking for the CBSE Term 1 crash course, you need to click on this link. After clicking on this link, over here you can select your plan, light or classic. The choice is all yours. For example, I want to take the light plan. I need to click on this buy complete course and use the coupon code WSPRO and give my number, give my email ID on which I get the OTP and everything, right? Yes? Okay. Similarly, there are a few more links as you can see over here. If you want to be with us, if you want to get trained by us for the NEET 2023, do click on this one, NEET 2 years, click on this link. After clicking on this link, you'll be getting a lot of plans. Light, Classic, Plus, right? Over here, you've got both the options. Either you can buy the complete course or you can go for the 1 month pro subscription. You can see how the actual Vedantu platform looks like, right? Okay, this is the complete course fee. No need to pay this much amount in one go. You can pay this much amount in installments as well. And at the same time, if you want to try it out for a month, click on this one, give your number, give your email ID on which you get the OTP, right? So people, this was all from my side in the tonight's session. I'll see you guys again at 10:30 p.m. on Vedantu JEE English channel, in which I'll be continuing with the chemical equilibrium, right? Tonight at 10:30 on Vedantu JEE English channel, I'm going to see you all, right? Till then, you take care. Bye-bye. God bless you all. Love you all. And do let me know in the comment section which chapter you want the next, right? Take care, guys. Bye.